Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 13P, word problems on spectacle lens magnification, thickness, slab off, and anti-reflection coating. Question 1. What is the percent magnification of a spectacle lens with a power of plus 8 diopters, a front surface power of plus 12 diopters, a center thickness of 4.5 millimeters, an index of refraction of 1.5, and last but not least, a vertex distance of 15 millimeters? Round your answer to the nearest tenth. So let's see what we know. We have the back vertex power is plus 8, the front surface power is plus 12. Thickness is 4.5 millimeters, which is 0.0045 meters. The index is 1.5. Vertex distance is 15 millimeters, which equals 0.015 meters. The magnification formula for spectacle lenses equals 1 over 1 minus CF1 times 1 over 1 minus VF prime V. We'll plug in our numbers. C is equal to the thickness divided by the index, thickness in meters. And the vertex distance also has to be in meters. That equals 1 over 0.964 times 1 over 0.88. And that equals 1.037 times 1.136. And we have the magnification then equals 1.179, which means the percent is 17.9% magnification. Question 2. Calculate the edge thickness of a minus 10 diopter meniscus lens index 1.523, whose surface power is a plus 4 diopters and minus 14 diopters. The lens is 44 millimeters in diameter, has a center thickness of 0.6 millimeters. Round your answer to the nearest hundredth millimeter, and we'll do it both with the exact and the approximate sag formulas. So the power is minus 10, the index is 1.523, F1 is plus 4, F2 is minus 14. The diameter of the lens is 44 millimeters. That means H, which is the semi-diameter, is 22 millimeters. Thickness is 0.6 millimeters. Now, in order to solve this problem, we need to first calculate the radii of curvature. We use those to then calculate the sag, and we use the sag then to calculate the thickness. So the first radius of curvature is n prime minus n over f1. N prime is the index to the right of the surface, n is the index to the left of the surface. R2, n prime minus n over f2. So the index on the right is air, 1, and the index of the lens is 1.523. Now we get a radius of 37.36 millimeters. Now we'll figure out the exact sag. The formula is S1 equals R1 minus the square root of R1 squared minus H squared. Plug in our numbers. And we find the sag equals 1.86 millimeters. Now we'll find the sag of the second surface. Plug in our numbers. And we get the second sag is 7.16 millimeters. Now the formula for a negative meniscus lens, a concave meniscus lens, the center thickness equals the edge thickness plus S1 minus S2. So if we rearrange the furniture, we get E equals T minus S1 plus S2. We're solving for the edge thickness. We plug in our numbers, and we find that the edge thickness using the exact sag formulas equals 5.90 millimeters. Now let's see what happens when we use the approximate sag formulas. Approximate sag equals h squared over 2r. So S1 equals h squared over 2r sub 1. Plug in our numbers, and we get our sag of the first surface is just about the same as the sag that we found exactly. S2 equals 22 squared over 2 times 37.36 and equals 6.48 millimeters. A little different from the exact sag. We plug in our numbers to find the edge thickness. We find it equals 5.23 millimeters. We subtract the two findings and we find we're off by 0.67 millimeters, hardly anything. Question 3, calculate the slab off required if the powers of the right and left spectacle lenses are planosphere -1 cylinder axis 180 and -3 sphere respectively. So we have our right and left optical crosses. If the cylinder is axis 180, the power is 90 degrees away in the 90th meridian, and a -3 sphere has -3 all over. So we figured out our powers in the 90th meridian. You can forget about the minus sign. What we're concerned with is the direction of the base. Prentice's formula is power equals power times the decentration. Decentration is 1 centimeter, so the prism power is 1 prism diopter base down. For the left lens, again, the decentration is 1 centimeter, so the power is 1 times 3, or 3 base down. And it's base down again because a concave lens, when you're looking through the bottom of the lens, it's like looking through a base down prism. So the slab off is done in the more base down lens, that's the left lens, and there'll be the difference of 3 minus 1, or 2 prism diopters slab off in the left lens. Question 4, what percent of the incident light is reflected off the surface of A high index lens of index 1.65, and B, a plastic lens of index 1.49? Round your answers to the nearest hundredth. So the formula for percent reflection equals 100 times n minus 1 over n plus 1 squared. We plug in 1.65 for the index. And we find that the percent reflection off the high index lens is 6.02%. Now we'll plug in for the basic plastic lens of index 1.49. It's made of the same plastic that you find in your toothbrush handle. We find the percent reflection is much lower. It's 3.87%. And that's why high index lenses often have anti-reflection coatings, more likely to have them. Question 5, what is the ideal index of refraction of the anti-reflection coating that is placed on a lens with an index of 1.6? Round your answer to the nearest hundredth. So the ideal index equals the square root of the index of the surface that the coating is put on, equals 1.27. So wouldn't it be nice if we could coat our bodies with an anti-reflection coating? If we don't reflect any light, we become invisible. The Invisible Man did that exact thing, and he went to visit his busy doctor. And the Invisible Man walked up to the receptionist, and she was a little startled, of course, when he first spoke to her. But he said, I'd like to speak to the doctor, please. So the receptionist went on the intercom and said to the doctor, the Invisible Man wants to talk to you. And the doctor answered, tell him I cannot see him now.